Greetings everyone, my name is Aleksandar Pajkanovic and I teach several courses in electronics at the Faculty of Electrical Engineering, University of Banja Luka. It is my pleasure today to present the topic of free IC design in education. Basically, I will be sharing some experiences that we collected over the last several years in using the free resources to create the IC design curricula at the university. I'll first provide a quick introduction and the motivation that lies behind this work and the general idea. Then we'll dive into looking at why do we actually need the tools, what's all the fuss about, why do we need the PDK, and then we'll discuss the possibilities and opportunities with non-free and free tools, pros and cons. For those of you not into IC design, I'll explain what PDK is in just about a minute. So the CMOS fabrication, the CMOS IC fabrication, the IC being integrated circuit, is the most sophisticated technology process commercially available on Earth. Therefore, it is not an exaggeration to say that its importance is paramount in the education of every generation of electronics engineers in the years to come. So that puts sort of a burden on our shoulders, the educators in the area of IC design, in a way that we have to find a way to bring IC courses to the universities, but in a way that students get actual real-world silicon-proven experience. That's not an easy task, and main obstacles are actually paperwork, and as it has always been with the university's funding. So one of the aspects of this paper will be a revolution that is happening as we speak, and I'll talk about that in the later part of the paper. But for now, let's just say that the main points in time are when the first chip design using only the free tools was fabricated, basically silicon proven, and then the next moment is when the first PDK was when a first open sourced PDK appeared in public last year. So what I'm trying to say is that with this, there are no more excuses. Basically, we have to make sure that every electronics student should work on a real-world example during the studies. The general motivation behind this work, and this work is actually just one of the smaller pieces in a larger puzzle, but basically the general motivation between our efforts in providing the free IC design in education is to learn, build, and grow upon the fact that mature nodes perform very well in so many areas where low cost, low power consumption, and stability are of interest. We also want to join the effort to demonstrate real silicon examples designed using open tools. We also want to popularize these tools, the technology, and electronics in general. And as a sort of summary, we basically want to build a world-class university level course at zero or close to zero investment. The motivation for this particular paper is to share our own experiences from teaching free and open source analog and digital IC design at the University of Banja Luka. This paper is based on what we have right now, but in case there are people interested in how we actually come to this point and when the phases that we went through to actually come to achieve what we have right now, quite a stable program for both of the courses, analog and digital. You can find that in these papers published across the last 5 or so years. So the three main things that need to meet together to actually have the IC see the sun is the idea, the tools, and the PDK. So the idea is basically the schematic, the topology, what we want to realize. The tools are the software applications that we have to use to prepare the files such that an IC may be implemented based on that. So where circuit theory produces files that are manufacturable. And then the PDK is actually an abbreviation of a project design kit, and that's basically the summary, the collection of the data related to devices that the factory can fabricate. So this contains models and information of the devices such as transistors, diodes, resistors, and so on. And then when we work on an idea within the tools to solve a problem, we have to use this information in order to make our results achievable and our design manufacturable. So the tools, the silicon foundries, these came a bit later, not at the beginning of IC design. So if there were no tools and no silicon foundries, we could say that we wouldn't have any problems. However, back in the 60s and the 70s, like half a century ago, when the whole storyline of the integrated circuit design started, the designers and some of the legends, some of the pioneers are shown on the right hand side, Bob Weidler and Yanis Tsevidis. They would have to make the circuits work in an unproven technology. They had to lay the circuits manually on a light table, and basically they would have to produce chip themselves in the lab. Since there is no silicon foundry, there are no tools, they would have to work with dangerously high temperatures and poisonous fumes. Privileges such as working with a simulator would be just a dream for most of the people. Fortunately for the Berkeley crew, right next door, the first simulator was being developed at the same time, so they had this opportunity back then to use the punch cards to simulate circuits. So once the potential of ICs was recognized, the market exploded, creating further markets like consumer, industrial, military, electronics, and so on. And therefore, this need for using the computers, of course, powered by the advance of the PC, and again, that was also powered by the advance of IC and spiraling each other. This created this whole industry of electron design automation, or computer-aided designs. These are abbreviated with EDA or CAD tools. So this industry created a new struggle to come up with a tool capable of following the technology process. By today, we have 3 vendors well established, and their commercial licenses per seat per year are well into 5 or even 6 figures. They all do provide discounts for higher education and startups under certain limitations, and yet that still requires funding, and paperwork is by far no less in these cases. So why do we need the free tools? Well, we need the free tools because industry standards are so much expensive, for even cutting-edge technology processes are in question, and we would like to be able to work with the IC not encumbered by this feature of we want to work with older nodes that are capable of functioning properly, but we don't want to spend so much money on tools. So the free tools have been around since the 80s, but they're pretty much unusable in practice, or they have been unusable in practice for the following 2 reasons. First of all, they wouldn't support the new technology nodes, and that's not an easy task. It's not an easy job to support the development at the rate that these new nodes were dictated. And also the silicon foundries became a commonplace by the 80s, so neither one of these silicon foundry is basically a factory that implements in physics, in the physical substrate of silicon or whatever other technology might be in question. The plan, the design that the circuit designer created using the tools. So if a silicon foundry, if the factory, or sometimes you call them just fab, does not support the tool with their PDK, does not provide the information of their devices in a way that the free tool can recognize, this information, then basically the tool is useless. There are some ways around it, but they're not really around it. They're still encumbered by different problems. For more details, please contact me or just look online. So anyway, whatever that may be, we still are subject to NDAs, and fabrication still must be paid. So what changed in about the last 10 years or so is this company, eFabless, took up the fight to actually bring the free tools to the point that they can actually be usable to create fabricable, manufacturable silicon. This has been built upon several projects sustained by Tim Edwards and some other well-known free tools such as ngSpice and Yosis and so many more. So basically, for the last few years, we already have a fully functional toolchain available at no cost, and also without any documentation, apart from honoring the open source license. So we would still have to obtain the PDK under an NDA, and the major limitation here is that such design would not be an open hardware. This great breakthrough has been achieved by Tim Edwards. The first IC designed only by free tools has been fabricated, and this is called Raven, a small digital system. Very soon more people join forces, and the most prominent project being ASIC1. They created this bandgap reference. I'm hoping to see some results. And we were also fortunate to take part as well, among the first in the world. For more details, please check the Indel 2020 paper, where we, together with the students at our department, designed two integrated circuits using one of the XFAB nodes, working with only free tools. This was thanks to Edmund Hammenberger and Symbiotic EDA, and of course great support from Tim Edwards. So to revisit the three things that we spoke, when we have the free tools, the only thing that we need to create free open hardware down at the nanoscale level is basically we just need the PDK. So that's exactly what happened in June 2020. The Skywater 130 nanometer CMOS PDK has been open sourced. That basically sorts out our first problem, the paperwork that I brought up, and then the thing that also is really important is that the other problem has been solved as well, at least for the time being, is that Google is actually funding fabrication for open source design. So there were already 2 runs, so fabrication of silicon designed using free tools and using the free PDK is free of charge with Google Shuttle runs. We're hoping that there will be more of these. Here are some information about the devices from the Skywater. I wouldn't go into these graphs. They're just a nice way to show how we can provide very relevant information very quickly with the scripts that we developed here in Banja Luka, which are also available online for free. We have 2 courses, and we have created analog circuit design course, where since this is the first time that students are working with these tools, we first have to take them on a journey through Linux, Python, and Spice, and then we take care of devices and modeling. Then we take them through these new tools, the schematic entry, the layout tool, magic, and so on. As far as theory goes, we work with the basic amplifiers, and then we move on to advanced simulation techniques, advanced layout techniques, matching, and we finish with the design of the operational amplifier. For more details on the operational amplifier, please check the paper we published just recently, just a month ago at MEAL conference. As far as the digital circuit design course is concerned, we have decided to move on to develop a processor course, and the first core that we developed from scratch is Hack. For more information, please visit this nant.tetris.org. At some point this was taught at Stanford, and then we moved to Berkeley, figuratively speaking, because we start learning Chisel. Chisel is a hardware construction language as opposed to the Verilog or VHDL, which are standard hardware description languages. For more details on Chisel, RISC-V, and in general everything shown in this slide, please check out the IC Hetran 2021 paper that was also published just a couple of weeks back. Just years ago, this was impossible to imagine. We have our students using real PDK with actual tools that can provide silicon-proven design, so we get to work on a real-world example that we hope also to fabricate. And we have already done one fabrication with XFAB with the help of funded by Symbiotic EDA and through Europractice, and we hope to spread this further and develop further. This is the point where I would like to show my respect and send out a warm thank you to all those who made this happen. This also brings a great responsibility. As I said, there are no more excuses. We have to at least try to provide all our students with the possibility to work on real-world silicon-proven examples. Of course, the three things that I spoke about are, of course, a big deal. However, what I found extremely important is to keep in touch with people who excel in this area for so many years. Keep an eye on labs, homeworks, and projects from Berkeley, Stanford, and MIT. That's a very good practice. We hope to, in the next semester, we hope to upgrade the digital design toolchain to go for OpenLane instead of Qflow. That's kind of becoming a standard now, and we want to include the OpenRAM tool as well. We are expecting to get involved in the third MPW funded by Google. All our contributions are available online, so the scripts, the graphs, the everything. And thank you for your attention. Please contact me if you have any further questions. This is my email. I would like to discuss this or any other topic, and of course the possibility of collaboration. Thank you very much.